Okay.
Can you see my blackboard?
Yes, I can see it.
Yeah. Okay. First of all, yeah, I put the YouTube links here, but from the last lectures, I just sent the lectures here, the PDF files, and also put the YouTubes here. So again, so then I will not update these things. So every lectures I put the PDF and then the also YouTube files. This is the homework 3 I put in here. So you can download it. I want to put the homework for today, but for the next Thursday, because this homework has 3 problems only. And the next homework for today, you want to, and that if you want to assign the new homework day, it has also 3 problems. And then if you go to the assignments tab in your Blackboard, then you can see that's homework 3 due 9/22, okay? And the homework 4 would be 9/24, right? Just, okay, so that's about the Blackboard course. So just I want to make sure you, every lectures, once you find the lectures, also you can find the YouTube files here. Okay. Does it make sense to you?
Yes, thank you.
Mm-hmm. And so let's see, go to the, so today we wanna, so last lecture we wanna talk about one important application that was indeterminate beam and determinate bar. And also, let's see the other application, again, that's a indeterminate case, but if you have under the, for example, thermal effects, right? So let me write, here thermal effects, all right? So if, for example, we have some object, and do you remember about the formula if you have the thermal change, temperature change, and coefficient of the thermal? Do you remember the formula to find the elongation? Maybe you remember from the physics. Do you remember that? For example, if you have something like this, right? It has a L, and then if delta T is the temperature change, right? And we have something alpha is coefficients of thermal expansion, right? So then we have, you can find this coefficient for any material, some things in the appendix. So then delta, if we add a temperature here, right, then it may be elongated or something like that. So then delta L, if you remember, we have this formula, right? Do you remember this? From the physics, alpha delta TL, right? We are not looking for to prove this one, but in the physics, we know that if you have a thermal effect, so if you temperature change, right? And then if this is a length of the length of the something like bar, and then delta T alpha is coefficients, then we can find the delta L, something like that. And then now if you're back to the mechanics of the material, for example, in the mechanics of the material, we talk about the strain, right? And the strain, if you remember, is delta divided by L, right? So in this case, delta L divided by L would be alpha delta L alpha delta T, right? So in case, we may not ask you to calculate the strain, but in case if you are asked to what's the strain when we have a thermal effect, and what's the strain? The strain just will be alpha times delta T, right? That's a strain. It's a strain, right? That's the formula for a strain, and just I substitute instead of deltas alpha delta TL, right? So, but now let's go back to that problem in last lectures. What happens if you have some indeterminate bar? Let me indeterminate bar, something like that. For example, you know, indeterminate bar, we have two supports here, like just assume an easy case. I want to show you one example later, but now just for the that's a bar with two fixed support, and then we maybe increase the temperature, right? If we increase the temperature, then right, we want to find based on that, we want to find, for example, the reaction on this support, right? For example, if this is A, this is B. Let's see, if, for example, this is RA, this is RB. We want to find this one, right? So again, that's indeterminate. So just look at this one. So we know the summation of force in direction of X is just RA plus RB. And now for this example, yeah, just look at, there is no any other forces, just like that, right? But the temperature change, which means the bar wanna expand it, but these two supported don't allow the bar to expand it, then it makes some reaction, right? Reaction in this support, right? Reaction and the stresses. But the problem is we are not able to find RA and RB because only one equations, right? So the same as the last lecture, the best approach to solve this one is just the principle of superpositions and employing the equations for the elongations, right? So again, let's just let's assume something like this. Let's assume like that. We have this bar, right? I want to use superposition, right? First of all, let's assume we don't have this support, right? We don't have in this support. And just under the thermal temperature change, we may have some elongation here, right? Based on temperature, right? And then, but also we have some, the reaction here, right? Let's just also add the reaction here. Let's see, RB, right? So, which means we remove the support only based on the temperature, right? In last lectures, we set some forces here. We say based on those forces, but in this lecture, we don't have any external force. We have just temperature, right? And plus, without anything, without any forces, without any temperature, but actually this case, it has reactions, right? RB here, RA here, right? And then just we draw the free body diagram for this one, right? So then we can say this is a structure 1, this is a structure 2, right? And now I want to ask you the question for a structure 1 only under temperature, right? For this one, what is delta? In structure 1, what is delta?
Just alpha delta T times.
Right, alpha alpha delta T. I write this formula, just alpha delta TL, right? The length of this bar is L, the length of this bar, right? So that's enough for this structure. So for structure number 2, let's just find the delta, right? Only one segment. Just make a sections. It's very easy, right? It's RB. Let's say is FAB. So this is delta 1, right? Delta 2. So summation of force in direction of x0. FAB minus RB is 0. FAB is negative RB. And then delta 2, for example, is FAB, LAB, EAB, AAB, right? FLAB is negative RB, LAB, just L, just the length here is L. And just since we have one segment, just let's E and A, right? We don't need to write the index because we have only one, right? So then delta 1, delta 2. So what's next, guys?
We add them together.
Add them together, equal?
Elongation
Equal
total.
to 0.
Equal to 0, right? Because in reality, we have a support here, right? You have support here. So delta 1 plus delta 2 is equal to 0, right? Delta 1 is alpha delta TL minus RBL EA equal to 0. So we can find the reaction RB. RB would be alpha delta T AE, right? How can we find RA? RA from this equation, right? From this equation, we can find RA. And RA is the negative alpha delta TAE. So it's look like this. If you have this bar, the LAE, right, under alpha delta T, and then, okay, it's look like this, right? Alpha delta TAE, and this support alpha delta TAE, right? RA, RB, this is A, this is B, right? Just make sure this A is section area, cross section, this A is just point. It would be better maybe to show with the capital letter, but a small letter, little letter, but I forgot, okay? So, yeah, before going to the example, actual example, just about, this is a general, very, very general case. Does it make sense to you?
Yes, it does.
Right. So let me now write examples. I would like just you help me to solve the problem. It's very similar to the previous problem, but we want to focus on the effect of the temperature, right? So let's see, we have something here. let's see. Okay, indeterminate bar. So the diameter of this one is 1 inch. The diameter of this segment is 2 inch. Let's see, let's put, this is A, for example, this is B, this is C. The length of the segments would be 8 inch and 10 inch. So, and then, okay, let's for the segment A, B, oh, okay. Okay, E for all the segments, loss of modulus would be 10 times 10 to the 6 psi, and alpha would be 12.5 times 10 to the negative 6. Let me ask a question. What is the unit of alpha? Do you remember? Or
Is it over degrees Fahrenheit?
yeah, 1 over Fahrenheit, right? The reason, let me show you here. Here, you know, for example, delta, for example, would be inch, right? For example, so this L also inch. So delta T is Fahrenheit. So since this is inch, for example, and this is inch, for example, and this is Fahrenheit, then this, the unit of this should be canceled at this one, right? It's Fahrenheit times 1 over Fahrenheit, then it cancel, then inch times nothing would be this one, right? Does it make sense to you? So, because it should be consistent, that equation, right? This is inch, we know this is inch, this is Fahrenheit, so alpha would be 1 over Fahrenheit. That's a degree, right? That's a unit. So, in this case, let's see, right, alpha E, what about, okay. Find reactions given a temperature change delta T equal 70 degree Fahrenheit, right? So delta T is 70 degree, okay? So before, okay, we need, okay, how many segments do we have?
Two.
2 segments, the diameter is given. Let's also find, okay, before solving the problem, let's find the cross sections area, right? Let's, for AB would be pi times 2 inch over 4. Then would be 6 inches square, right? And A for, let's BC is pi this would be 0.785 inches square, right? So again, it's indeterminate. We wanna use a superposition, which means, first of all, release these supports and find the elongation just based on the temperature, and then we find the deformation based on reaction of this, and then add together and is equal to the 0, and then we can find the reactions, right? So let's see. So the purpose is when I use the superposition, okay, we can do like that. So let's see, for this case, we just use RC. So in general, we want to find the reactions. Reactions would be RA. Let's see, RC here, right? And for this case, this is called structure number 1. This is a structure number 2. So we have alpha, delta, T, and this one just find based on these external forces, right? So let's start structure number 1 with together. Can you please help me if, okay, if this is under the, if this is under this temperature, right? So then we have maybe some delta, right? Let's denote, for example, delta T. T means temperature, right? How can we find the delta T? Anybody?
3 times alpha delta T.
Right. You have 2 segments. So alpha delta TL for each segment, right? Your formula you are saying right, alpha delta TL for each segment. Let's for this segment plus alpha delta TL for the second segment, right? Let's see. Alpha for the first one is 12.5, 10 times -6. The good thing is this, alpha and delta T will be the same for, it is 70. What is LAB?
2 inches. Oh, sorry. 10 inch.
Length, 10 length, right. This is 10 inches. And this is 8 inches, right? Times 10 plus this one. What's delta T is 70 times 8, right? If you just add these terms together and then just multiply these terms together and then add, the answer I have in my note is 0.01575 inches. Guys, let me say something to you. Once you have this type of calculation, if you have all the numbers, for sure the answer should be a small number. Make sure if once you do with your calculator, because in reality, the delta alpha is a small number, and then delta TL is some value. When we multiply together, alpha is the order of -6, right? So the final answer would be something like that, something between 0 to 1. If you got a very huge number, for sure you have some mistake, because I saw the people use a calculator, maybe they forgot 10 to the negative 6 and just multiply or something like that. Then they reach the huge number, right? Just make sure, look at your answer. It should be reasonable because the elongation would be a very, very little number, right? The elongations. So that's a delta T for this one. And now let's find the formation for structure number 2. Structure number 2. And now let me ask a question. For structure number 2, how can we find delta elongation?
Is it PL over AE?
PL over AE, but we have
Twice?
two segments, right? We should first maybe use this segment and then this segment, right? Let's see, for segment BC, we have something like that, right? RC, FBC, right? If summation of force in direction of X0, FBC is negative RC, right? And okay, delta would be okay, FLIE for BC, right? So just help me to write. F is negative RC, right? What is L?
8 inches.
8 inches, right? What is A?
0.785 inches square.
Right. What is E?
10 times 10 to the power 6.
Right. Okay. I don't have the calculation for this. Just leave it. This one, then let's say B. For AB, we have like that. I'm writing all the details for the problems, right? Summation of force in direction of X. FBA would be negative RC. Let's see, delta BA would be FL over AE, BA. Okay, FBA would be negative RC. What is L?
Ten inches.
10 inches, thank you. What is A?
3.146.
3.146, and E is the same. We have the same material. Okay, that's so. Let's delta would be the total delta would be delta BC, delta BA. Okay, guys, just add these two terms together, and then the answer I have would be use your calculator. The answer I had this one, right? Okay. So what is the next step?
Equal to 0.
Yeah, we have this delta from this structures, from the second structure, and also we have this delta from the first structures. We should add together, right? And then equal to 0, because in reality we have the support here, right? Which means the deflection is 0, right? So delta T plus delta is 0. What is delta T? 0.01575, we find, right? Delta is negative 0.34 times 10 to the minus 6. RC is equal to 0, right? And RC would be the 11,780 pounds. So, okay. And you find these reactions. And RA plus RC equals 0 because of the equilibrium, right? At the beginning, you can write here if you want. If not, you can write at the end. It doesn't matter. We know RA plus RC is 0, right? Because of the equilibrium. But since we have one equation and we are not able to solve both, just we did all these calculations. Now RA plus 11,780 equals 0. So RA is negative. This is that direction. This is that direction, right? So we have final configuration, something like that. RC is this one. RA is this, right? Does it make sense to you? Question? A question?
Do you have an example where the reactions are not equal to each other?
Mm-hmm. If you have a problem, something like that, for example, if you have maybe, we have bar, and this is like this. If you have also force here, right? Or maybe other forces here, then we have some multiple segments, right? And then for sure, for example, if this is 100, this is 200, right? If this is RC, for example, this is RA, let's B, for example. And then we can say, okay, because of the equilibrium, RA plus RB is 300, right? Right? If you solve this type of problem, for example, then RA and RB is not necessarily equal, right?
Okay.
Mm-hmm. Then you have make a segment here, make a segment here, make a segment here. And it's the same as the previous lectures. But here in this case, right, we have some more calculations. But for sure, RA and RB may not be equal, right? So I will give you one homework problem today for this, something like this, for thermal. The next thing, okay, we have one more thing. Actually, we want to talk about something about the shearing strain. So before going to the next, for the next chapters, we want to go in the next chapter, torsion, next week. But there is one more thing we want to talk about. A little bit about modulus. So we know about the modulus of elasticity. A little bit we want to talk about modulus of rigidity and to say what does that mean. Solve the small problem for that, and that was for, you know, because for the rest of the semester, usually most of the semester we talk about the normal stress, but now let me a little bit talk about also the shear stress, and that was, you know, for that. So let me first, just again, draw a bar with the formula for deformation and stress, and then based on that, say what happened instead of normal force if you have shear force, what happened for the modulus between the relation between stress and strain, right? So let's, for example, let's just again, just back to this famous figure. If you have, for example, normal force here, so we know is under this one. It's maybe have a deformation here, right? So which means if this point is here, then this point goes there, right? Something like that, and then we have this deformation, right? So already we know this formula. We know the stress is what? N divided by A, right? We also know a strain is delta divided by L if the length of the bar is length, right? The other formula we talk about said what the stress-strain relation, right? This formula, right? E is modulus of elasticity, right? So we already know about this. But let me redraw again this figure. And see what happened if in a slot N we have a shear force here, for example, V, right? The same length here. So then, okay, we can say, okay, this point, let's see, for example, this point, for example, is P. Based on the shear, this would maybe jump up here, right? So first of all, let's just write the equation for shear stress. Shear stress is V divided by A, right? So we already know this formula. But for the deformation, we said, okay, let's see if this point P just in the middle, then point P maybe goes there. So guys, I am showing you the large scale, but actually P and P prime is very, very, very close to each other. Even here, for this problem also, I'm showing the large scale, but this delta is very, very small value, right? So based on the shear force, we can find the shear stress, and then how can we define the shear strain? Here we set a strain. This strain here in the left-hand side actually is a normal strain, but we said, okay, yes, a strain. But the strain based on the shear could be measured like that, right? The recipe is like this. Just add another line here, and then look at this angle. Let's this angle as gamma, right? And then we can say, okay, this angle is gamma, and the distance between P and P prime. Here we define delta, but now here let's just define as a distance, right? The vertical displacement, right? Therefore, the shearing strain would be, we showed this based on gamma, gamma, and gamma is delta over L. So we call this one shear strain. This is normal strain, but just we said strain because for most of the application, when we say strain, it means this one. Then we don't say normal strain, just say strain. But when we say shear strain, means this one. So you know this is the shear stress. Again, here we said stress. This is normal stress. What we said just stress, right? Question. Gamma is yes, gamma could be the angle, but you know, and this is L, right? Gamma is the angle, but you know, we are talking about the elastic region, and in elastic region we have a very small deformation, which means gamma actually would be, when we said the, if you look at this triangle, right? Actually sine of this angle is delta divided by L, right? But since this angle is very small, this gamma, right? Then gamma equals sine gamma equals tangent gamma, right? Then the gamma it would be delta over L. But you are totally right. Gamma could be the angle, could be the, so the shear strain would be the angle, right? Delta, this one, divided by length. But here, delta in direction of the length over L, right? Does it make sense to you? Okay, thank you. So yeah, these parameters, shear strain or something like that, is not a very big deal. It's not very important, especially in the design, in the application, because in the application, if these conditions satisfy the normal stress and the deformation in the actual, if it's satisfied, for sure, these conditions also satisfy. But in the aspect of the research, if you wanna continue as a research later, goes to master program, PhD program, maybe there are lots of research defined based on the shearing stress and something like that, right? But for the application in the work, so these are not a very big deal, these things, right? So let me just solve the one problem. One problem, we have, I try to draw nicely. Let me, okay, because I want to draw in 2D direction, and then set. If you have something like this, just look at these things. You have this block. This could be a block, right? You have one plate here and the other plate here. This plate is fixed to the ground, and this plate could be moved based on this force P, right? Let's see, this is 8 inch. This is 2 inch. And also, if you look at this, if you look at from top of the plate, the dimension of the plate would be like that. 8 inch, and the other direction perpendicular to the plane would be 2.5 inch, right? Okay. So, okay. Okay, if we, let's write something like that. If, for example, we have a reference point here, let's see this point, for example, P, right? Here. Okay, once we apply this force, right? Once we apply this force on this plate, and then this plate maybe jumped to the right, and then P goes to this point, would be P prime, right? Then P prime is given. P prime is given is measured actually as 0.4 inches, right? So PP prime equal 0.44 inch. Okay. So now you know there's a plate here. You apply the force and then it's moved. So in these conditions, we wanna find the shearing strain. Let's see the shearing strain, and maybe this is part A, right? And part B, find the force P exerted on the upper plate. So, okay, guys, I need add something. I forgot something is very, very important. Actually, these are the two important things, but now, I forgot something. Let me, where can I write? Maybe here I just add. So guys, this is not a big deal. Maybe here is would be better. I wrote here. Okay, here, so sigma n over a, tau v over a. Strain delta over a, this is strain delta over a. We have one more thing, a strain relationship, right? Sigma E epsilon. What is E? E is
Modulus of elasticity.
right, modulus of elasticity, right? Also, we have some relation here. The relation, let me write with the other color. We have tau stress times something times a strain, and then that calls modulus of rigidity. Modulus of, this is another question, right? Okay, modulus of elasticity for the normal and shear strain, modulus of rigidity or shear modulus. We can say modulus of rigidity or shear modulus, both the same. So, okay, in this problem also, modulus of rigidity or shear is called G is given. So, modulus of rigidity for this example, G is equal 90 KSI. Okay, these are the problem. So okay, let's go. So can you give me what is the shear strain? If you look at the shear strain formula and look at this figure, it's very, very simple. What's that? What do you think? Look at this angle, right? This angle is gamma, right? So, and this is 0.04 divided by this length, right? Look at this one. This one, look at something like bar and the force here. This figure is similar to this figure, just I rotated 90 degree, right? Just assume rotate this figure 90 degree. That V could be P, and this is length, right? So for part A, let's solve part A. Shear strain would be delta 0.04 divided by, what is L?
Is it 8 inches?
L, no 8. Look at this bar.
Oh,
2
2.
inches.
2 inches, right? Because force, now this the deformation in perpendicular to the length, right? The same as here. Look at the original shape. The delta is perpendicular to all, right? That's a shear. So divided by 2. 0.02. Okay. How about for part B? How can we find the force P? What do you think?
G times gamma.
Tau, okay, yeah, you are close. Yeah, for part B, tau is G times gamma. So we have gamma, we have G, we can find tau. And tau is just force divided by area, right? Okay, let's find tau. G is 90 KSI, let's multiply 1000 means KSI to PSI, right? This means KSI to PSI. And times gamma is 0.02 would be 1800 PSI, right? Okay, and now we know the formula for tau. Tau is P divided by A. And now I want to ask a question. Okay, tau is 18. P, can you give me what is A? What should I write for A if you look at this figure? A
20?
is
20 inches?
20. How?
2.5 times 8.
Okay, yes, 20. 8 times 2.5. The area of the plate, right? The area of the plate, right? Cross sections area, and cross sections area is 8 times 2, right? Because the surface is rectangular, right? 8 times 2.5. Therefore, P would be 36,000 pounds. Or you can write based on kilopounds, right? Does it make sense, guys? To you? Let me back here to make sure all of you can write the calculations. Does it make sense? Okay.
Professor, what's the K?
Okay. Kilopounds.
Oh, kilograms.